Right. Right. Okay. Right on. Hey, we're doing P1 notes. You asked why we doing P4 yesterday and P1 today. It's all review. Okay, so we could do P7 first if we want. It doesn't matter. We did P4 yesterday because it was going to take us longer than P1. P1 we could do in 2 months. P4 we wanted to give you 3 months or so. That's why that we flipped it around. Tomorrow we're doing P4. Nope. P3. We're doing P3 tomorrow. So obviously. Okay. All right. Awesome. So we're going to talk about real numbers today. So what we're doing, P1 is called representing real numbers. So let's talk about real numbers. So we have this little diagram with real numbers. And this is typically when we do math, we usually work in the real number realm. Sometimes we work out of it, and we're going to talk about this. All right. So I have a couple people drawing it, so I'm going to pause just a second. I want to write it down. Thank you. We're going to start inside and work our way out. Okay, so when I look at this picture, I'm like, oh, okay. So if I start the big one, real numbers, these things called rational and irrational are both real numbers, and the deal. And then inside this rational numbers, I got a smaller set of integers, even smaller set of whole numbers, even smaller set of natural numbers. So they get smaller and smaller and smaller. What are natural numbers? No, they're not decimals that go on forever without no pattern. You're thinking of something different. That is something different. Okay, but that's not natural numbers. Another name for natural numbers are counting numbers. What are counting numbers? Start counting, please. 1, 2, 3, exactly. That's exactly what natural numbers are. They're like when you count, they're 1, 2, 3, 4, ... going on forever. Okay, so that's natural. Next one are whole numbers. What are whole numbers? Numbers without a decimal, close, but not a cigar, because there's lots of numbers that are numbers without a decimal that aren't whole. Okay, say it. Good, all positive. Okay, plus the number 0. So whole numbers are actually 0, 1, 2, 3, 4. Okay, you guys are thinking way too hard. All right. Now let's talk about those sets. How many natural numbers are there in the set of natural numbers? How many are there? 10 of them? 15? 100? How many? Infinite, right? How many whole numbers are there? 10, 15,000? Infinite also. Which one has more? Doesn't whole numbers have more? Because they're natural numbers plus the number 0, so they have one more number in it. Wait. There are infinite amount of numbers in there. How can it be one more than infinity? That's a good thought, isn't it? All right, put that thought on hold. What are integers? Half of you are thinking of it. Say it, please. Not just positive, negative numbers, positive, negative whole numbers. Okay, we haven't started with decimals yet. Positive, negative whole numbers, nice. We use, the letter used for integers is Z. I don't know why they use Z either. Okay? It's just always used the set for Z as integers. -3, -2, -1, 0, 1, 2, 3. How many integers are there? Infinite. Compared to whole numbers and natural numbers, how many integers are there? Say it. Double. Isn't there twice as many integers as there are whole numbers and natural numbers? Right? Because for 1, there's also a -1 with the integers. For 2, there's also an integer. It's twice as big. Twice as big as infinity? That's an interesting concept, isn't it? That's too much for the second day of school, isn't it? Got a whole bunch. Awesome. All right. So those are the numbers that we like to work with, right? We like to work with the whole numbers. And when we talk about numbers, I say pick a number. You say like 4 or 9 or 32, right? Typically you pick a natural number or a whole number. You're okay with negative, so, right? We can deal with negative whole numbers. So we're comfortable there. Now, what are rational numbers? Oh, that's when we include all those other numbers that are whole numbers. Right. So, definition of rational numbers is any number that can be written as a ratio of a over b of 2 integers where b does not equal 0. Give me a second to write that and we'll talk. So it says to be written as a ratio of a over b. So what does that mean? Any number that can be written as a fraction. Okay? So give me an example of a rational number. 2/3. Fantastic. Thank you very much. There's an example of a rational number. Give me, whoops. I don't like that. Let's do it. Nope, didn't want to go there. That's good. Really good. Really good. Cool. Yeah. Give me a rational number that's not a fraction. Give me a number that can be written as a fraction. It's not a fraction. 0.5, 0.123. I'm going to go with 0.5 because we can write that as what? I have. Okay. Give me a number that's rational, that's not a fraction, that's not a decimal. Pi is not rational because it goes on forever. That decimal terminates. 3. Can't I write 3 as a ratio? 3 over 1, right? I can write any integer. Okay, so those are all rational numbers. And we got one more in there that we haven't represented. That's also rational. That's just like 3. I like the thought. The comment up here was 0. -3, that's integer. Okay, just like 3. Okay. I like the thought. How about, what's another way to write 2/3? 0.6 repeating, right? We can get those decimals that go on forever also. So any decimal that goes on forever with a pattern, though. So decimals that terminate, decimals that go on without a pattern, whole numbers, fractions. Those are all rational numbers. That's most of the time what we work in, right? We typically, in our life, we talk about rational numbers. We typically talk about whole numbers, then we deal with money, $1.75. That's a rational number. Okay, so that's where we're at. All right. Then we have these other things, so that's all that. Now think about how many rational numbers are there compared to natural numbers. Holy cow, there's a lot of those, aren't there? That set is huge. I mean, it is infinitely large. Oh wait, so is natural. Huh, interesting. Okay, let's talk about irrational numbers. I have these irrational numbers over here, pi, square root of 7, square root of 3. Notice I don't have the square root of 4 over there, or the square root of 9, because we can take those square roots. So it's not just any square root, but it's a square root that we can't take. Okay, any square root that's not a perfect square will be a decimal that goes on forever without that. Okay? Those are irrational numbers. They do not overlap with rational numbers. They're completely separate. My favorite definition of math is irrational numbers. Definition of irrational numbers: real numbers that are not rational. Thanks. That tells me a lot. Tells me what they're not. Doesn't tell me what they are. I think I could have got that from the name. Irrational. Oh, they're not rational. We have a bunch of examples of those up in our picture, right? Pi, square root of 7. When we put those two sets together, notice how they are completely separate. When we combine those two sets together, we get the set of real numbers. Majority of the time in this class, we're going to work with real numbers. Majority of the time in life, you work with real numbers. Actually, starting to have to work with rational numbers, but we can get those irrational. We're going to work most of the time with real numbers. Well, and now it's 2 you learned numbers that weren't real. What were those called? Imaginary numbers. Okay, so we got somewhat, there are more numbers than just this. Right? We got this other set that sits completely outside of this real number thing called imaginary numbers, or we call them pure imaginary numbers. And then when we put those two together, the imaginary numbers together with the real numbers, that gets the set of complex numbers. And that's all the numbers that we know. Boy, there's a whole lot of those. How many complex numbers are there? Infinite, right? Compared to natural numbers, there's a whole lot more complex numbers. Still infinite. Makes me think. Real numbers. Oh, any number that can be written as a decimal. Okay. I just say what's a real number? It's a rational number, or a rational number, or irrational number. Good there with sets and real numbers. Any questions on any of those? Just wanted to give you an idea of what sets look like and what numbers. You know, you guys know what numbers. You know, you've been working with counting numbers since before kindergarten. Right? That's where we started, and we're still working. All right. Change gears completely. Okay. This chapter P is all over the place. Remember, it's Algebra 1, Geometry, and Algebra 2 all put into one. Things that you need to know for pre-calc. So we're all over the place. Okay? So there's P1, talk about some numbers. Now we're going to talk about graphing on numbers. Just want to remind you of something. All right? You already know this. Remember inequality and interval notation? The one that's, I think, a little newer that we're doing well with, Algebra 2, is that interval notation. Remember those parentheses or brackets sort of deal? Okay. All right. So, if I have the inequality x is greater than 3, I want to go from 3 to infinity. I use the parentheses compared to a bracket on the second one, because I'm not including 3. On the second one, I'm including 3. All right. Now, over here for our graph, if you remember our graph, I have 2 graphs. I have usual graph in your book. Your book does something different than the usual graph. So I want to make sure you understand what happens if we use our book and you see in your book and you're like, what's that graph all about? It's not very difficult. Okay. So if I want to do things x greater than 3, I'm going to go 0, I'm going to go 3, I'm going to do an open circle, and I'm going to shade to the right. We are comfortable with that, aren't we? All right. Your book is going to do this. Your book is going to put a 0 on there. It's going to put a 3 on there. But instead of using an open circle, they're going to bring this notation of a bracket, of a parentheses over to your graph. And instead of an open circle, they're going to do a parentheses on that 3 and shade to the right. They're the only authors I've ever seen deal with this parentheses bracket on the graph compared to open close circle. I think ACT, college entrance exam, all those fun trade tests that you're going to be taking next year too, so is going to do open and close circle. Okay. So when we graph things, we're going to graph things open and close circle. Just if you look in your book and you see that, that's what's happening. So on B, where x is less than or equal to 3, notice I have the bracket on 3 because I want to include it. The other thing I want to point out is this. Whenever we write interval notation, we always do the smallest, then the big. Small, comma, big. So negative infinity is smaller than 3. So I went negative infinity to 3. Up here, we went from 3 to infinity. 3 is smaller than infinity. So it's always, always, always small to big. Small, comma, big. So 0, 3, close circle, less than. What's your book going to do? 0, 3, bracket, and to the left.
So you're in here for a month?
Yeah. All right. Last one. Sorry, second to last one. Let's remember written like these. Second to last graph, I should say. Okay. A lot of you are going to read this as 1 is less than x is less than or equal to 3. Correct. Let me see if I can make it easier for you. Okay. When I read this, when I see this, it's called a compound inequality. 2 inequalities in 1. When I see this, and when I write this compound inequality, always the smaller number on the left, bigger number on the right, and always use less than symbols, maybe a less than or equal to. But I'll read it this way. X is between 1 and 3, including 3. Because I'm seeing my variable is between 1 and 3. Well, on my graph, I want to go between 1 and 3, open circle on 1, close circle on 3, and I want to shade between. So it just kind of makes sense to me. Instead of reading 1 is less than x less than or equal to 3, I read x between 1 and 3, including 3. What's your book going to do? Yep, you already know what your book's going to do. Parentheses, brackets, shade. Okay? Good? All right. You guys try this one real quick. Go. Any number at least 7. Write it 3 different ways. Graph it, I would just do it. Open circle or close circle. So I went close circle above 7. I went x greater than or equal to 7. At least 7, 7 or bigger. Good? Questions? So now, change gears again. Okay? We went from set notation to graphing, inequality, interval notation, to exponents. Holy cow. Lots of stuff in P1. In your book, and there's a link on Canvas, if you want to, we can give you a book. We very rarely use it. We'll talk about it more than one. But there's a list of rules. I'm going to ask you guys to do number 1 and 2 right now, not by yourself, with your elbow partner. Talk to each other. Go. I didn't know that. No. Hey, I'm going to run out of time, though. We don't want to run out of time, do we? Okay. All right. First one's probably the hardest of the 4. Wasn't very nice of us to put the hardest one first. But get over it. So, hey, when I was walking around, I liked what I was hearing. You did a nice job. First one, I'm going to deal with the square outside. So I'm going to square the 3, 9. I'm going to square the a squared. When I have this power to a power, you were correct to say multiply the exponent. So that's b to the 8. That was accurate. Next one I'm looking at outside of this parenthesis. I'm looking out here. There's no exponent, so I just write it down. I like to write things down and try to do it all in my head. I do much better when I write things down. Now, since I have in my parentheses, I multiply the things out front. 9 times 5 is 45. Then when I see the same base, a squared, a to the 6, I add my exponents. That gives me a to the 8th. I add my exponents. 8 plus 1 on the b is b to the 9th. Good? Awesome. Number 2, I'm going to there's a couple ways to do this. Order doesn't really matter much on this. For me, I always deal with my negative exponents first. That's just me. Okay, you can do things. I heard a couple of you talking about subtracting because you're top to bottom, and you're thinking about subtracting exponents. I love it. Great. Okay, I will do that. But when I see that negative exponent, that's what I'm going to deal with first. So I'm just going to write down all the other stuff. I'm going to write down the a squared up top. I'm going to write down that ab cubed, because those don't have any negatives. And all I'm looking at is that b to the negative 2 right now. What do negative exponents do? Yeah, it takes that and moves it down to the bottom, doesn't it? Okay. So what it does, it changes the location of the base. Since I have a negative exponent up top, it moves it to the bottom. If my negative exponent was on the bottom, I'd move it up top. So that b squared comes down below. Now I don't have any negative exponents. Now I have a whole lot easier time doing that. So I'm going to look top to bottom with my a's. I'm going to subtract my exponents. So I'm thinking of 2 minus 1, which is 1. And there's more up top. So I have that a to the first power left up top. And I b with this down below. In my first class, a couple people left it as a b to the negative 5. We will never leave a negative exponent on our answer. So here, I would need to go one more step to get that same answer. If anyone was thinking about it. Okay? Don't leave negatives. Good? Awesome. Whoops. 3 and 4, your turn. Give it a try. No calculator. All right. See that negative exponent outside the fraction, it just flips it over. We call that take the reciprocal. So if I think about it, that 2 on the bottom goes up top, that x squared on the top goes on the bottom, and I have to square everything. So this gives me 4x over x to the 4th. Right, I was walking around, just about everyone had that. Okay. Last one, this is the hard one. Okay. Hey, when I have this 16 to the 3 halves, I have a rational exponent. That gives me a radical sign. Okay. So I have 16. Where's the 3 go? That's the power. Where's the 2 go? That's the index, exactly. That a whole bunch of you are looking or pointing up over here. That 2 goes there. Do we usually write it 2? No, because it goes as a square root. If it's a 3, a 4, a 5, or a 6, then we write it. But we typically don't write that 2 because it's an index of 2, so it's like I have that square root, so I'm going to get rid of that, but that's where that 2 went to. All right. So now, what's 16 cubed? Yeah, I have no idea either, right? I said no calculator. We could do that side by that's 16 times 16. That's a big number, and then multiply that. Holy cow, that's a really big freaking number. I don't want to deal with that. So how about we do this? How about we do the square root of 16 first, and then cube it? What's the square root of 16? That's 4, right? We can do that. And what's 4 cubed? Well, what's 4 times 4? 16 times 4. Yeah, I'm not real sure either. Let's see if I can make this easier for you. Instead of multiplying by 4, I multiply by 2 and then by 2. Because I can double just about anything. What's 16 double? 32, right? Half of us said that. And double 32. And that's a lot easier than doing 16 times 4, isn't it? Doubling it and doubling it? I think so. So that gives me 64. Okay? You know how I learned how to do that? I didn't use my freaking calculator. That's why those of you that use your calculator all the time, you don't learn those little tricks. That's called number 6. All right? We'll get you more of those. Good job today. Hope you have a wonderful day.